see, 25. All right, so today we'll begin chapter 3, which is operational amplifiers. Okay, operational amplifiers. So we saw the BJT, bipolar junction transistor, and we saw one of the functions, one of the most common applications of a transistor is for use as amplification. Okay, so amplifier functions, ideal amplifiers can basically perform signal amplification, filtering, and impedance isolation. So what exactly is an operational amplifier? Well, an op-amp is nothing but a transistor amplifier, but it's a special kind of transistor amplifier. It's created in a differential configuration. So at its most basic, we can say an op-amp is a differential amplifier. Differential amplifier. It amplifies the difference in two signals. The most common ways to construct would be like this. This is not an actual circuit, but this is just an illustration of how you can have two inputs in an amplifier. Okay. You don't have to draw this out. It's not. This is again just for explanation purposes. So you'd have V in 1 and V in 2. Okay, V in 1 and V in 2. So a operational amplifier, or op-amp for short, as they are more commonly known, is nothing but a differential amplifier created using BJTs, which we studied in chapter 2. And this results in having two inputs, V in 1 and V in 2. Okay. Some of the most common applications of this kind of circuit is, as I stated here, signal amplification. We can use it as active filters. Remember filters that you studied in, well, you haven't studied in 201, but the filtering applications of a capacitor and an inductor, right? We can add those capacitors to this op-amp circuit, and we can create a different kind of filter known as active filters. And then we can use them for impedance isolation. Some of the other applications, we use them for audio processing, measurements. In the lab, we'll use them as comparators. So you have a comparator chip in your lab kit. You also have an op-amp chip in your lab kit. Okay, so we'll use both. And then also oscillators for signal or function generation. So the same kind of, so the same circuit can function in multiple different ways, simply by the addition of a few external components. Okay. If you add a few resistors to that circuit, it becomes a amplifier. If you add a few capacitors in there, it becomes like a filter. So this is a circuit diagram of one of the most popular op-amps, which is model number IC741. Okay, 741. It's been around for decades. This is what I studied when I was a student more than 30 years ago. This is still what students study all these years later. Okay, IC741. And this is the internal construction of the IC741. This shows you the pin out configuration of the microchip package. Okay, it's more like output, input, input. Okay, and I'll explain more on the next slide. So again, you basically have a single piece of semiconductor, likely they're not silicon, and you construct all of these transistors and devices on the circuit. So it's a miniaturized PCB that contains all of these elements. And then simply by adding a few external components, you can use it for many different applications. Okay, many different applications. So what you're going to study is how can you use an op-amp as an off-the-shelf component, as a sealed box. All you're going to do is you take an op-amp. We are not studying the internals of the op-amp. You're simply taking the op-amp and we use that as a building block to build different kinds of circuits. Okay, so you're not studying the internals of the op-amp. Again, I want to be clear, we're not studying the internal circuitry of an op-amp. We are using that as a building block to create different kind of circuits. Okay, so this triangle right here is the symbol of an op-amp. It doesn't matter what kind of op-amp you're using, symbol remains the same. It's a triangle with an output on the right and you have an input to the left. In this case, of course, we have two inputs. They are marked, typically, they are marked with a minus and plus. So minus would be at the top, plus would be at the bottom. Now the image here is the opposite, but you have to be careful. Every image is not going to tell you what the inverting and non-inverting input is. It'll simply show you a plus or a minus sign. The plus sign is known as the non-inverting input. And the minus sign indicates it's the inverting input. V out is always taken at the end on the right side. So this V out or VO. What is not shown in here are the power supply inputs. The power supply inputs are typically here. And the reason they are not shown is because it sometimes complicates the circuits. Whether they are shown or not, they are present. Okay, so in the transistor circuitry, you can see there's a positive power supply there, negative power supply there. Okay, so the plus and minus sign here indicates the DC power supply that we connect to the op-amp. Plus VCC and minus VEE. The naming convention simply came from the fact that the power supply was connected to the collector of the BJT and the emitter of the BJT, hence plus VCC and minus VEE. In the lab, you would simply take this as a positive and negative dual power supply. So you'd create a dual power supply using two power supplies, apply the positive end to pin number 7, pin number 4, negative to 7. Or was it the other way around? Always keep forgetting that. Positive to 7, negative to 4. So again, whether the power supply terminals are shown or not, they are always present. If they're not shown, it's implied. Circuit cannot function without a power supply. So then we have two modes of operation, common mode and differential mode. Common mode simply means you're applying the same input to both terminals. V1 is equal to V2. And then there's differential mode, where it amplifies the difference between the two terminals. Okay, V1 minus V2. Non-inverting minus the inverting terminal. So that's the differential mode. And the special property of an op-amp is that it's a differential amplifier, so it amplifies the difference between the two input terminals. Okay, most of our circuits at their fundamentals, most of electronic circuits at its fundamental is basically amplifying the difference between two signals. So again, an op-amp is basically a differential amplifier. It amplifies the difference in signals between its two input terminals. This doesn't stand for America Online. A stands for gain of an amplifier. A is for gain. AV would mean voltage gain. And in this case, AV would be V out, or ratio of V out to V in. Okay, voltage gain AV is V out or V in. The OL stands for open loop. And the loop it is referring to is the output loop going back to the input. Be more correct, it's the output tied back to the input. Okay, so the loop refers to output to input. Okay, output to input. So in the open loop mode, meaning there is no connection between the output back to the input, this is the open loop, the gain for a op-amp would be infinite. That's one of the properties. And so AOL theoretically is infinity or infinite. Open loop gain is infinite. So it amplifies even a small difference in V1 and V2, and it sends to the output. So here are the properties of an ideal op-amp. An ideal op-amp will have infinite input impedance. Will have zero output impedance. Infinite gain in the open loop. Infinite differential gain. And then zero common mode gain. And also infinite bandwidth. Of course, all of this is not possible in real life circuits. Anyway, so it's infinite input impedance, zero output impedance, infinite differential gain, zero common gain, and infinite bandwidth. So input impedance is basically the resistance or the impedance as seen by the driving circuitry. Meaning if you are sending in an input signal, it presents an infinite resistance right at the input. Okay, because it presents an infinite resistance, the current draw is 0. In real life, of course, it's not infinite. It's a very large resistance. Current draw is not 0. However, it is very small. It is almost negligible. Okay, for many analyses, you will take it as negligible or close to 0. The same thing at the output. Output is 0, and so it provides infinite current, or as much as the load requires. Infinite differential gain, meaning very small difference between the input terminals, will be amplified with infinity. And common mode gain is 0, meaning if the same signal is applied at both input terminals, output is equal to 0. This is very important because noise signals that appear in any amplifier circuit or in any circuit would appear equally at both terminals. If the common mode gain is 0, that would mean that any noise signal that appears at both terminals would effectively not reach the output. And so it's one of the big advantages of having a differential amplifier. And then infinite bandwidth. Infinite bandwidth means it will have the same operation, it will behave the same for a wide range of frequencies. In reality, the op-amp does not behave like that. And this is frequency on the x-axis, and this is V out. Then after a certain point, performance of the op-amp will drop off. Okay, these are just the fundamentals. Again, this refers to no feedback open loop op-amp. Okay, all of the circuits that we work with will have a feedback. Okay, 7 minutes left. The equivalent circuit of an op-amp can be drawn like this. We have the non-inverting input at the top. And the inverting input at the bottom. So the difference VID is V1 minus V2. Then at the output, you have a dependent voltage source that provides you V out as a function of V in. VID is the differential input. Okay, differential input. Dependent voltage source, as a brief recap, it behaves as a voltage source. It supplies its rated voltage, except it is dependent on some other quantity. In this case, the dependency is on VID. Constant is AOL, the open loop gain. So it provides a constant voltage at the output as a function of the input. So next slide, I simply summarized the properties. Any questions so far? Okay. So this was just a summary of what I wrote out earlier. All right, again, with ideal op-amp. So at the input side, we can say Z in is infinity between the two terminals. And at the output side, we have the gain that is infinite. And then V out, of course, minus A, V2 minus V1. Now here, This image, V1 is referring to the inverting input. And V2 is referring to the non-inverting input. In the textbook, in quizzes and exams and homework, nothing will be stated. You'll have to extract the information from the image, right? When you look at an op-amp image, you will see a plus and a minus sign inside the triangle. Plus and minus sign inside the triangle indicates that they are the inverting and non-inverting terminals. The power supply terminals are external to the op-amp triangle. Okay, they may or may not be shown. If it's a circuit built with several components, then more likely than not, they will never be shown. Okay, even if they are not shown, they are always present. Okay. What does the minus sign indicate? Anyone? 180 degrees out of phase. As the name suggests, it's inverted. It doesn't mean anything else in this context. For voltages and for currents, we say it's the opposite polarity or the opposite direction. For amplification here, the minus sign indicates it's inverted or 180 degrees out of phase. So the input, if given to the inverting terminal, will be inverted at the output. In 2 minutes left, so I'll point this out. The output is, so the question being asked is how is the relationship defined? It's the output that is 180 degrees out of phase with the input. So if you apply the if we apply input to the inverting terminal, then the output will be 180 degrees out of phase. If we apply the same input to the non-inverting terminal, then the output will be in phase. So it would not be inverted. But the more important concept I want to talk about is this. Zin is technically infinity or infinite, the difference between the two. So if we apply any input to the terminals, no current flows in there. So if no current is flowing, then what is the voltage across this resistor, across that impedance? V equals IR. I is equal to 0. What is V? Zero. So voltage is 0. So the difference in voltage is 0 across these 2 points. Okay. So what if we ground one terminal, either the inverting or the non-inverting? If we connect it to ground, the voltage at one end or one inverting terminal or one terminal is 0. So what is the voltage at the other end? 0. So if it's 0 at both ends, we can say they are virtually shorted together. If one terminal is grounded, actually, let's first type out Zin is infinity. So oh, it's 1 o'clock. Same level. I is equal to 0. And hence we can say both terminals are shorted together. And so we say they are virtual shorted or virtual short. So if one terminal is grounded, the other one is grounded too. All right, we'll stop right here and pick up here again on Wednesday. This is known as the concept of virtual ground. All right.